Find somewhere comfortable tonight. You don't need to follow any of this closely. You don't need to hold on to the details or remember the names or keep track of where we are. Just let the words come in the way a tide comes in, quietly, without asking anything of you. We're going to travel somewhere very still tonight. Somewhere colder and quieter than anywhere you have ever been. Somewhere that exists right now in a small room on this earth where matter itself has been coaxed to the very edge of absolute stillness. If today was heavy, you can set it down here. Whatever you carried through the hours, the decisions, the worries, the things left undone, none of that needs to come with you into this next hour. You are allowed to be here, just here, horizontal and warm, while the world outside does whatever it does without you. We're in no hurry. The science we're going to wander through tonight is patient science. It took decades. It required people who were willing to wait. And the thing at the center of it, a tiny, ghostly cloud of atoms resting in a magnetic cradle, cooled to a temperature that nature never quite manages on its own. So settle in. Close your eyes if they aren't already. The words will find you wherever you are. To understand what happens at absolute zero, it helps to understand what temperature actually is. Not the number on a thermometer, not the feeling of cold air on your face, but what it really is underneath. Temperature is motion. That's the whole of it. When something is warm, its atoms are moving, jostling, vibrating, spinning, bouncing off one another in an endless, restless dance. The warmer a thing is, the more furiously its atoms move. A flame is atoms moving very fast. A block of ice is atoms moving slowly, but still moving. Even the ice, even the stillest, coldest thing you have ever touched with your hand is full of motion at the level too small to see. Absolute zero is the point where that motion runs out entirely, where the dance stops, where every last whisper of thermal energy has been removed, and what remains is the deepest stillness that physics permits. Imagine a large room at a party. It's warm in there. Warm because it's full of people, and people are always moving, always generating a little friction and heat just by existing in space. Now imagine the party slowly ending. People leave in ones and twos, and the room grows quieter. The conversations drop away. The movement slows. The warmth begins to fade. Absolute zero is not just when the last person leaves. It's when even the chairs have stopped vibrating, when the walls themselves have gone still, when motion in every form has simply ceased. There is a reason we call it absolute. It is the floor. There is no colder. You cannot go below it any more than you can go below the bottom of the ocean. It is the end of the scale in that direction. And in all the billions of years this universe has been cooling and expanding and arranging itself, nature has never quite reached it. Nature gets close in places, but close is not there. Here is something worth sitting with quietly. The coldest places in the known universe are not out in the vast darkness between the galaxies, where you might expect to find the deepest cold. Out there, in the empty spaces between stars, the temperature is still a few degrees above absolute zero, warmed by the faint ancient glow left over from the beginning of everything, a whisper of heat that fills the whole of space like the last ember of a fire that burned 14 billion years ago. The coldest places in the known universe are on Earth. In small, carefully built rooms, in university basements and national laboratories, in places lit by the blue glow of computer screens and the hum of vacuum pumps, scientists have created temperatures that are 1 billion times colder than the space between stars. Not a little colder, not significantly colder, 1 billion times colder. The number is almost impossible to hold in the mind, and yet it is accurate. At those temperatures, matter does not behave the way matter ordinarily behaves. The rules that govern the world you can see and touch. The rules that say objects have definite edges. that things stay where you put them, that two separate things cannot be the same thing. Those rules begin to soften. Something else takes over. Something older and stranger and, in its own quiet way, more beautiful. What takes over is the nature that every particle has always had, but that is normally hidden beneath the noise of warmth. Because every particle, every atom, every electron, every tiny piece of matter is not simply a hard little ball sitting in a fixed location. It is also a wave. It has a spread to it, a fuzziness, a tendency to be not quite here and not quite there, but somewhere in between. At ordinary temperatures, that waviness is so small as to be invisible. The atom seems like a solid thing in a definite place. But as the temperature drops, as the motion slows, as the frenzy of heat is gradually removed, the wave nature of each atom begins to grow. The atom becomes less like a grain of sand and more like a ripple on still water. And when the temperature drops far enough, something happens to those ripples that has no equivalent in the everyday world. They begin to overlap. And then, quietly, without drama, they merge. In a laboratory in Colorado in the summer of 1995, a small cloud of rubidium atoms, rubidium being a soft, silvery metal not unlike the potassium in a banana, was cooled to a temperature so close to absolute zero that it would require writing out a decimal point followed by 6 zeros before you reached the number. At that temperature, those atoms stopped being a crowd of separate individuals. They became something else entirely, something that had been predicted 70 years earlier by two men who never had the equipment to test whether they were right. That tiny cloud, held in a magnetic cradle no larger than a grain of rice, is where this story begins. In 1924, in the city of Dhaka, then part of British India, now the capital of Bangladesh, a young physicist named Satyendra Nath Bose was working on a problem that had been bothering him for some time. He was 30 years old. He was teaching at the University of Dhaka, a place that did not yet have the equipment or the resources of the great European laboratories, but that had, in Bose, someone with an unusually clear and patient way of thinking. He was interested in light, specifically in the way that light of different energies is distributed when something hot glows. The equations that describe this had been worked out years before. But Bose felt there was something unsatisfying in how they had been derived, a kind of circular reasoning buried inside the maths that he couldn't quite accept. So he worked out a new way of deriving them, and in doing so, he arrived at something he may not have fully realized was new, a different way of counting identical particles. This sounds like a small thing. It is not a small thing. In ordinary counting, the way we count everything in daily life, two objects are always two separate objects, even if they look exactly the same. Two coins of the same denomination are still two coins. You can tell them apart, at least in principle, by where they are. But Bose noticed that for particles of light, for photons, the tiny packets of energy that make up a beam of light, this assumption didn't hold. Two photons of exactly the same energy are not just similar. They are, in some deep sense, genuinely identical, interchangeable, indistinguishable in a way that goes beyond anything in ordinary experience. And when you count them as if they were truly, fundamentally identical, not just similar, but the same, you get different results, results that matched what was actually observed in nature. Bose wrote up his derivation. It was a short paper, clear and careful. He submitted it to a respected journal. The journal rejected it without explanation. So Bose did something that required both confidence and a certain graceful audacity. He wrote directly to Albert Einstein. Einstein was, by 1924, the most famous scientist in the world. He had already given physics the special and general theories of relativity. He had explained the photoelectric effect, the work that would eventually win him the Nobel Prize. He was a man receiving correspondence from all over the world, most of it easy to set aside. But Bose's letter was different. Einstein read it. He read it carefully. and he recognized in that short paper from an unknown lecturer in Dhaka something genuinely profound. He translated the paper into German himself, because German was then the language of international physics, and he arranged for it to be published in one of the most prestigious journals in Europe under Bose's name. Then he sat with the idea for a while, and then he extended it. Einstein asked, if this new way of counting works for particles of light, what about atoms? What about a gas of ordinary atoms, the kind that make up the air around you? Could the same logic apply? He worked through the mathematics and arrived at a prediction, a quiet, almost offhand prediction buried in a paper published in 1925 that would take 70 years to confirm. Cool, a gas of the right kind of atoms, Einstein wrote, to a temperature low enough, and something will happen. The atoms will stop distributing themselves across all available energies the way they normally do, the way gas molecules in a room spread themselves out across a range of speeds and temperatures. Instead, a large fraction of them will suddenly drop into the very lowest possible energy state, all at once, together. He called it a condensation, not a physical condensation, the way steam becomes water on a cold window, something more abstract, more quantum. A condensation of identity, a collapsing of separateness. The prediction was noted, it was discussed, and then, largely, it was set aside, because nobody at the time had any idea how to cool a gas of atoms to the temperatures required. The numbers were almost impossible. The coldest refrigeration available in 1925 could reach temperatures a few degrees above absolute zero, impressive for its time, but still enormously far from what Einstein's equations demanded. The gap between what was theoretically required and what was technically possible was so vast that the whole idea drifted into the category of things that might be true but could never be tested. It stayed there for a very long time. Decades passed. The Second World War came and went. The transistor was invented. Humans walked on the moon. The personal computer arrived. All of this happened, and the prediction sat, patient and unverified, in the archive of physics. Bose himself never worked on it again. He moved into other areas, became a respected figure in Indian science, was eventually nominated for the Nobel Prize multiple times without ever receiving it, which is one of the quieter injustices in the history of the field. He died in 1974. 21 years before the thing he had set in motion was finally confirmed. Einstein had been dead for 40 years by then. In 1995, two physicists named Eric Cornell and Carl Wieman, working in Boulder, Colorado, finally closed the gap, using techniques that hadn't existed when Einstein made his prediction, techniques involving lasers and magnetic fields, and a vacuum so complete it would make the surface of the moon seem cluttered. They cooled a small cloud of rubidium atoms to within a whisper of absolute zero, and the condensate appeared. They saw it in their data as a sudden, sharp peak, a pile-up of atoms all occupying the same state at the same moment, exactly what Einstein had described, exactly what Bose's counting had made possible to predict. A few months later, Wolfgang Ketterle at the Massachusetts Institute of Technology did the same thing independently, using sodium atoms, and was able to study the condensate in more detail. In 2001, all three men shared the Nobel Prize in Physics. It is one of the longer gaps between prediction and confirmation in the history of science. 70 years of waiting, of the idea sitting quietly in the literature while the technology slowly, patiently caught up. There is something in that worth noticing, the way some truths are simply ahead of their time, not wrong, not forgotten, just waiting for the world to be ready for them. The question of how you actually do it, how you take a cloud of atoms and remove almost all of their heat, is one of those rare cases where the answer is both deeply strange and, at its heart, surprisingly simple. It happens in two stages, and the first stage uses light. Not heat from light, not the warmth of a lamp or a flame, quite the opposite. Lasers, which are very pure, very focused beams of light, can be used to slow atoms down. And slowing atoms down is, as we've established, the same thing as making them cold. Here is how it works, told as simply as it can be. A photon, a single particle of light, carries a tiny amount of momentum. When it strikes an atom and is absorbed, it gives that atom a tiny push. The push is almost nothing. It is vanishingly small. But if you arrange your laser beam so that it is pointing directly at a moving atom, aimed straight into the atom's face as the atom moves toward the laser, then each photon that gets absorbed nudges the atom backward, slows it down, just a fraction. Now do this thousands of times a second with 6 laser beams arranged so that they push back against the atom from every direction, left, right, up, down, forward, backward, and the atom finds itself in what physicists describe, with some warmth, as optical molasses. It is surrounded on all sides by a gentle opposing pressure, a resistance to motion in any direction, and it slows. The whole cloud of atoms slows together. The temperatures achievable this way are already extraordinary. Starting from room temperature, laser cooling can bring a cloud of atoms down to something in the range of 1/1,000,000th of a degree above absolute zero, written as a fraction, that is 1 part in 1,000,000. The cloud is already colder at this point than anything that exists naturally anywhere in the observable universe. But it is not cold enough. To reach the temperatures where the condensate forms, to get down into the billionths of a degree, you need the second stage, and the second stage is something you have almost certainly experienced yourself in your kitchen or on your desk without ever thinking about it as physics. It is evaporative cooling. When a hot cup of tea sits on a table, it cools, not because something cold is being added to it, but because the hottest molecules at the surface of the liquid, the ones moving fastest, carrying the most energy, escape into the air as steam. They leave, and when they leave, they take their energy with them. The molecules that remain are, on average, slightly less energetic, slightly slower, slightly cooler. The tea settles to a lower temperature. This is exactly what happens in the second stage of cooling a condensate. The laser-cooled cloud of atoms is held in a magnetic trap, a carefully shaped magnetic field that acts like a bowl, confining the atoms to a small region of space. The trap is then adjusted so that it is just slightly too shallow at the edges. The fastest atoms, the hottest ones, the ones with enough energy to climb the sides of the magnetic bowl, spill over and escape. They drift away into the vacuum. The remaining atoms, the cooler ones, redistribute their energy among themselves and settle to a lower average temperature. Then the trap is made shallower still. More of the hottest atoms escape. The cloud cools further. And again, and again. Each iteration removes the most energetic atoms and leaves behind a colder, denser, quieter group. The cloud shrinks as this happens. You begin with perhaps 100 million atoms in your trap, and by the time you have cooled to the temperatures needed, you might have 100,000 left. You have sacrificed most of your atoms to cool the rest. It is a patient, iterative process, not unlike the way a long, slow night removes the heat of the day, degree by quiet degree. What you are left with after all of this is a cloud of perhaps 100,000 atoms held in a magnetic cradle in the middle of a vacuum chamber so empty that it contains almost nothing else. It exists in a space smaller than the full stop at the end of a sentence. The temperature it has reached is so close to absolute zero that the gap between them, the tiny remaining sliver of warmth, is almost philosophical rather than practical. And in that cloud, something is about to happen. The atoms are still. They are slow. Their wave nature, which has been growing as the temperature has fallen, has stretched to the point where something remarkable is becoming possible. The waves of neighboring atoms are beginning to touch. Every atom has two natures. It has a particle nature, a location, a mass, a definite existence in space, and it has a wave nature, a spread, a tendency to exist not at a single sharp point, but smeared across a small region, like a sound that fills a room, rather than coming from one exact spot. At ordinary temperatures, the wave nature is so small, so compressed by the heat and motion, that it is effectively invisible. Atoms behave like tiny billiard balls. They collide, bounce, scatter. They have addresses. You could, in principle, point to one atom and say, "That one, there." But as the temperature drops, the wave nature grows. This is not a metaphor or an approximation. It is one of the genuinely strange facts about the universe at its smallest scales. Each atom's wave, its spread of probable locations, physically expands as the atom cools, the way a sound grows in a room as it reflects off the walls and fills more space. At the temperatures reached by laser and evaporative cooling, the waves of individual atoms have grown large enough that neighboring atoms' waves begin to reach each other. Think of it as ripples on a still pond. Each atom is a ripple, spreading outward from a center. As the pond grows quieter and quieter, the ripples grow larger. And when two ripples meet, they don't simply collide and bounce back the way billiard balls do. Waves do something different. They overlap. They add together. They become, for a moment, one larger wave. Now imagine this happening not to two atoms, but to 100,000, all at once. There is a critical point, a specific temperature below which the waves have grown just large enough to touch their neighbors on all sides, and at that point, something changes in the whole character of the cloud. It is not a gradual transition. It is a phase change, the way water suddenly becomes ice at a specific temperature rather than gradually becoming more solid. One moment, there is a crowd of separate atoms, each with its own wave, each with its own identity. The next moment, there is something else. The waves merge, all of them, into one. What exists after this moment is a single unified wave that spans the entire cloud. Every atom in it is no longer a separate individual with its own location and its own motion. They have all fallen into the same quantum state, the same rhythm, the same phase. The cloud has become, in a very real physical sense, one object. Scientists call it a superatom, a cloud of perhaps 100,000 atoms behaving as though they were a single particle, a single wave, a single thing. There is an image that might help carry this. Think of a large crowd of people in an open space, each one moving at their own pace, in their own direction, breathing at their own rhythm. The crowd is full of individual noise and individual motion. Now imagine that. Very slowly, as the night deepens and the crowd grows tired, the movements begin to slow. Individual rhythms begin to align. And eventually, Bose-Einstein, that is the condensate. The technical name for this state, a Bose-Einstein Condensate, named for the two men whose work made it possible to predict and understand, describes a gas of particles of a particular type, particles that are, unlike electrons or protons, willing to share a quantum state. Electrons are famously territorial. No two of them will occupy the same state, ever. But other particles, the kind that make up light and that include certain atoms when their internal structure adds up in the right way, have no such exclusivity. They are, in a sense, generous. They will all pile into the same state if the temperature is low enough to encourage them. Rubidium atoms, the ones used in that first 1995 experiment in Colorado, are of this generous type. So are sodium atoms and lithium and hydrogen and several others. Each one, cooled far enough, will surrender its individuality and join the collective. What the researchers in Colorado saw when their condensate formed was a sudden sharp spike in their measurements. A pileup of atoms, all at the same energy, all at the same location, all behaving identically. On the graph, it looked like a mountain appearing from nowhere, a sudden peak where before there had been only a gentle slope. It was the signature of 100,000 separate things becoming one. The experiment lasted only a few seconds before the cloud warmed and dispersed. But in those seconds, something existed on Earth that had never existed before, something that Einstein had predicted from a desk in Germany, based on a letter from a lecturer in Dhaka 70 years earlier. Once the condensate exists, it does things that ordinary matter simply does not do. Things that feel less like physics and more like a dream about physics, the kind of dream where the usual rules apply right up until the moment they don't. The first and perhaps most immediately strange property is superfluidity. The condensate, if it contains the right kind of atoms under the right conditions, can flow without any friction at all. None. If you set it moving inside a container, it does not slow down. It does not lose energy to the walls or to itself. It continues indefinitely, the way a pendulum in a perfect vacuum would swing forever, except that a perfect vacuum is an approximation and a superfluid is not. More than that, a superfluid will climb. If you place a superfluid in a container, it will creep up the inside walls, over the rim, and down the outside, draining itself until the container is empty. This is not a trick or an illusion. It is the consequence of having zero resistance to flow. Every path that leads to lower energy is taken, even the ones that involve flowing uphill. The superfluid finds the lowest point available to it and moves there, regardless of what is in the way. It will also flow through gaps that no ordinary liquid could pass through, gaps that are, by any ordinary measure, sealed. The condensate passes through them as though the barrier were not entirely there, which, in the quantum sense, it is not. These properties are not unique to Bose-Einstein condensates. Liquid helium, cooled to just a few degrees above absolute zero, also becomes superfluid, and this was known and studied for decades before condensates were created in the laboratory. But the condensate makes the quantum origin of superfluidity visible in a way that liquid helium, being a dense liquid rather than a dilute gas, does not. In the condensate, you can watch the quantum nature of matter express itself in slow motion, under controlled conditions, in a way that lets you understand not just that it happens, but why. Then there is the experiment with light. Light, in a vacuum, travels at the fastest speed anything can travel. It would circle the Earth several times in a single second. It is, by any ordinary measure, the fastest thing there is. And yet in 1999, a physicist named Lene Howe and her team at Harvard University used a Bose-Einstein condensate to slow a beam of light down to 17 meters per second, roughly the pace of a bicycle. 17 meters per second. Light, moving at bicycle speed. The experiment worked because of the way the condensate interacts with the light passing through it. The condensate, being a single unified quantum object, responds to the light in a collective, coherent way, absorbing it, holding it briefly, passing it forward, and this collective response slows the light's effective progress through the cloud to a tiny fraction of its ordinary speed. It is as though the light is not simply passing through the condensate, but being passed, hand to hand, through a very dense and very cooperative crowd. Howe and her team then went further. In a subsequent experiment, they slowed the light to a complete stop. They stored it inside the condensate, a pulse of light held in a small cloud of atoms, as still and quiet as a firefly caught in a jar. Then, when they were ready, they released it, and the light moved on, carrying the information it had contained through the brief moment of its stillness. Stopping light, not blocking it, not absorbing it permanently, but pausing it, holding it in place, and then releasing it intact. This is the kind of sentence that should probably not make sense, and yet it happened in a laboratory, and it has been repeated many times since. There is one more phenomenon worth visiting, and it has a name that captures something of the gentle humor that physicists sometimes bring to the very strange corners of their field. Under certain conditions, a condensate can be made to briefly collapse inward and then explode outward. A tiny silent implosion followed by a tiny silent expansion, releasing a faint burst of energy and a small spray of atoms into the vacuum. The pattern is, in miniature, reminiscent of the way certain dying stars collapse and then burst outward in a stellar explosion. Researchers, with a kind of fond amusement, called this phenomenon a Bose-nova. The name is partly a pun, Bose for the condensate's co-predictor and nova for the stellar explosion it resembles, and partly an acknowledgement that something genuinely new is happening, something that sits at the intersection of the very small and the very large, the quantum and the cosmic. A cloud of atoms, cooled to almost nothing, briefly imitating the death of a star. The universe, it turns out, has a way of echoing itself across scales. There is a problem with making a condensate on Earth, and the problem is gravity. Gravity is gentle. You don't notice it most of the time, in the sense that it is simply the background condition of being here. But for a cloud of atoms cooled to within a whisper of absolute zero, gravity is not gentle at all. It pulls the atoms downward, compressing the bottom of the cloud, making the density uneven. The atoms on the lower side of the trap press against one another slightly more than the atoms on the upper side. This pressure adds a tiny amount of energy to the system. And at these temperatures, tiny amounts of energy are not tiny at all. They are significant fractions of the total thermal budget of the cloud. In other words, gravity puts a floor on how cold and how still a condensate on Earth can become. In orbit, this problem disappears. On the International Space Station, that metal habitat drifting in a continuous fall around the planet, roughly 400 kilometers above the ground, everything is in free fall together. The station, the equipment inside it, the air, the people, and any atoms held in a magnetic trap are all falling at the same rate, following the same curved path around the Earth. Nothing presses down on anything else. The effective gravity inside the station is, for practical purposes, zero. In June of 2020, NASA activated an instrument called the Cold Atom Lab aboard the International Space Station, a small, refrigerator-sized device that had been installed and tested over the preceding years and successfully created a Bose-Einstein Condensate in orbit. It was the first time a condensate had ever been made in space. The difference was immediately apparent. Without gravity pulling the cloud downward, the magnetic trap could be made much weaker, and a weaker trap means the atoms can expand more freely. And when atoms expand freely, they cool further, the way a gas cools when it is allowed to expand into a larger space. The condensates created in orbit were able to reach temperatures even closer to absolute zero than those made in the best ground-based laboratories. They were also able to do something that ground-based condensates cannot easily do. They were allowed to simply drift, expanding outward slowly in all directions without being pulled into an asymmetric shape by gravity. The cloud bloomed. It spread outward in a slow, perfectly symmetric sphere, growing larger and colder as it went, like a soap bubble expanding in slow motion, or a single thought becoming gradually more diffuse in a quiet mind. The shapes that formed, the spatial patterns of the expanding condensate, revealed details of the quantum structure that had been obscured on the ground. Without gravity distorting the picture, the underlying order of the condensate became visible in a way it had never been before. There is something quietly remarkable about this that goes beyond the physics. The Cold Atom Lab is, right now, running experiments above us. As you lie here in the dark, somewhere overhead, perhaps passing over your part of the world at this very moment, there is a small device aboard a station in orbit, holding a cloud of atoms in a magnetic cradle, cooling them toward the deepest stillness that nature permits. The coldest things in the known universe are circling the planet in the dark, a few hundred kilometers up, held in a structure built by human hands. The experiments being conducted there are aimed at fundamental questions: the nature of gravity at the quantum level, the behavior of matter in conditions that simply cannot be replicated on the ground. Condensates in orbit have been used to test whether the fundamental rules of physics hold equally for all types of atoms regardless of their mass. A question that goes back to Galileo's observation that a heavy ball and a light ball dropped together fall at the same rate. The condensate in space allows this to be tested with a precision that no previous experiment has achieved. But beyond the specific results, there is something in the image itself that is worth holding gently as you drift. Something about the contrast between the enormous dark silence of space and that tiny humming cloud of atoms at its most fundamental stillness. Something about the fact that the most delicate and quiet thing humans have ever made is not locked away in a vault or stored in a drawer, but is out there, drifting, circling the whole world in the dark. The story of Bose-Einstein condensates is not a story with an ending. It is more like a river that has been followed to a certain point, and beyond which the water continues, and new tributaries keep joining from unexpected directions. In January of 2026, a team led by a physicist named Sebastian Will at Columbia University in New York published a paper in the journal Nature, announcing something that the field had been working toward for years: the first condensate made not from single atoms, but from molecules. A molecule is two or more atoms bonded together, and molecules are, in important ways, harder to cool than single atoms. They have more internal complexity. They can rotate, they can vibrate, they can bend, and all of those internal movements carry energy that has to be removed before the molecule can be cooled to the point where its quantum wave nature takes over. The challenge is something like trying to get a group of restless people to all sit still, when each person also has fidgeting hands and a tapping foot that have to be stilled separately before the whole body can be quiet. Will's team worked with molecules made of one sodium atom bonded to one cesium atom. Sodium and cesium are both atoms that had been used in condensate experiments before, but the molecule they form together is more complex and more richly structured than either atom alone. Cooling these molecules to condensate temperatures required a careful sequence of steps that had taken years to develop. The condensate they created formed at a temperature of roughly 5 billionths of a degree above absolute zero. It lasted for 2 full seconds, an unusually long time for a condensate, which typically exists for a fraction of a second before warmth from the surrounding environment dissolves it. 2 seconds was long enough to study its behavior in detail, to watch how it moved and responded, to begin to understand the richer quantum landscape that molecules, with their greater internal complexity, open up. A molecular condensate is interesting for reasons that go beyond simply extending a record, because molecules can interact with each other in ways that single atoms cannot. They have an asymmetry, a positive end and a negative end, like a tiny bar magnet. The quantum phenomena they exhibit are richer and stranger than those of atomic condensates. The physics becomes more complex, more varied, more capable of modeling the kinds of quantum systems that arise in materials, science, and chemistry. Then, a few months later, Will's team found something else. When they adjusted the way the molecules in the condensate interacted with each other, using carefully tuned microwave radiation to change the effective attraction between them, something unexpected happened. The condensate didn't simply change its shape or temperature. It collapsed inward and formed droplets. It collapsed inward and formed droplets. Not a single droplet, but many. Tiny, dense, self-contained spheres of ultra-cold molecular matter, each one 100 times denser than the condensate had been before. And these droplets were stable. They held themselves together with no container, no trap, nothing to confine them but their own internal quantum forces, the same weak attractions between molecules that, at ordinary temperatures and scales, would be far too feeble to hold anything together. At these temperatures, those weak attractions became, relative to the tiny thermal energies involved, something much more significant. The droplets simply sat there, self-bound, in the vacuum. It is a strange image. Tiny, dense spheres of matter, each one a coherent quantum object, floating freely in empty space, held together by nothing but their own nature. No wall, no container, no cradle. Just the quantum forces between molecules, balanced so precisely that the droplets neither expand nor collapse, but simply persist. Meanwhile, in France, a different group of researchers was using the condensate for a very different purpose. In March of 2026, physicists at a French research institute used a condensate of ultra-cold helium, cooled to 25 billionths of a degree above absolute zero, and illuminated it with a carefully designed laser pulse. What they observed in the condensate afterward was a pattern of excitations, tiny disturbances rippling through the quantum cloud, that mirrored, in miniature, a process believed to have occurred in the very first moments of the universe. In the earliest fraction of a second after the beginning of everything, the universe was not filled with matter. It was filled with energy, with quantum fields, with something closer to pure potentiality than to the solid, particle-filled cosmos we now inhabit. Matter, as we know it, was born from that field, particles flickering into existence from what had previously been empty space, drawn out by the enormous energies of those first moments. The French experiment recreated this process in a quiet and miniature way inside a condensate. The laser pulse played the role of those early energies. The condensate played the role of the quantum field, and the excitations that appeared, the tiny ripples in the cloud, were analogous to the particles born from the vacuum at the beginning of time. It was, in a sense, a time machine, a quiet pool of ultra-cold helium sitting in a laboratory in France, gently reflecting the oldest question in physics: where did matter come from? The condensate, it turns out, is not just a curiosity or a record-breaking achievement. It is a lens, a way of looking at questions that are otherwise inaccessible. Questions about the nature of quantum fields, the origins of the universe, the behavior of matter in conditions that no longer exist anywhere in the natural world. Each new condensate experiment is a new angle on the same deep question. What is the universe, at its most fundamental level, actually made of? The answers are still coming in, slowly, patiently, one cold cloud at a time. We have traveled a long way tonight, from the image of a crowded room slowly emptying, to a young man in Dhaka writing a letter that would change physics, to laser beams gently stilling clouds of atoms, to 100,000 separate things becoming one, to light stopped in its tracks and held like a caught breath, to a device drifting in orbit above the dark earth, to molecules forming self-bound droplets in a French laboratory, to the echo of the first moment of the universe rippling through a pool of ultra-cold helium. And at the center of all of it, there is one image that keeps returning, one quiet, persistent image. A small cloud of atoms, held in a magnetic cradle, cooled to the very edge of absolute stillness. It is worth sitting with what absolute zero actually means now that we have come this far. Not the number, not the technical definition, but the idea beneath it. Absolute zero is not emptiness. It is not the absence of everything. A condensate at the coldest temperature ever achieved is not a void. It is the opposite of a void. It is matter in its most ordered, most coherent, most unified state. All the chaos has been patiently removed, the random jostling, the individual trajectories, the noise of separate identities, and what remains is something pure. Something that has found, through the patient removal of everything unnecessary, a deep and fundamental agreement with itself. The atoms in a condensate are not absent. They are present in the most complete way possible. They are present together, as one. There is a parallel here that you might notice if you are still awake or half awake, or somewhere in the soft space between. A mind full of the day's concerns is a warm gas. It is atoms moving in all directions, colliding, scattering, each thought pursuing its own trajectory, generating heat and noise in its passing, the worry about tomorrow. The memory of something said this afternoon, the list of things not yet done, each one separate, each one carrying its own small energy. But a mind settling toward sleep is a cooling gas, the thoughts slow. They lose their sharpest edges. The individual trajectories become less distinct. The noise drops away, not all at once but gradually, the way a room cools after the last person leaves. And somewhere in the depths of a good night's sleep, perhaps, there is something like the condensate, a state where the separate threads of thought have stopped competing and started, very gently, to align, where the mind is no longer a crowd but something quieter and more unified, where the sharp distinction between this thought and that thought has softened into something more like a single, still field. You don't have to reach absolute zero tonight. Nobody does. Even the physicists in their laboratories never quite get there. Nature has a flaw, and approaching it asymptotically is the best anyone can do. The point is not to reach the bottom. The point is to move in that direction, to slow, to let the most energetic parts of the day escape, the way the hottest atoms spill over the edge of the magnetic trap and drift away into the vacuum, taking their restlessness with them. The atoms that remain are the ones that settle. Right now, in a laboratory in Boulder, Colorado, or Cambridge, Massachusetts, or aboard the International Space Station drifting somewhere above you, there is a small cloud of matter held in a magnetic cradle, cooled to a temperature that has no natural equivalent anywhere in the universe. It is quieter than the space between the galaxies. It is stiller than anything that has ever existed without human intervention. It is 100,000 atoms that have given up their separateness and become, for a few precious seconds, one thing. It hums in its way, not audibly. But there is something in the idea of it, in the image of that tiny cloud resting in its cradle, that carries a kind of quiet companionship. Somewhere tonight, matter is resting as deeply as matter can rest. The universe's most energetic and restless substance has been patiently, lovingly stilled. You have been patient tonight too. You have carried the day this far, and it is done now. The day is behind you, growing distant the way a sound fades when you move away from its source. The thoughts that were sharp a little while ago are softer now. The list of things is still there, somewhere, but it is not here. It is in tomorrow, where it belongs, waiting quietly. The condensate in its cradle, the cold cloud in the dark, the 100,000 atoms breathing as one. And so we leave it there. Somewhere behind you, the day is already distant. Let it stay there. Drift now, if you're ready. Sleep well.